So we're going to be talking about ACP-75, which is talking about acceptance proofs. So yeah, let's get right into it. Why do we want acceptance proofs? Most consensus protocols natively produce something that we call like acceptance proofs or finalization proofs or something kind of like similar along these lines. But the idea is that it is some kind of like succinct, compact proof that lets you say that this block was accepted by consensus. And so once consensus is performed, the proof is generated, and then you don't have to, like re-perform consensus to re-verify that a block was accepted or not. So by using this like proof, once consensus is performed, you can reduce your dependency on consensus on an accepted block, and then therefore also reduce the load that a validator has to serve, since consensus doesn't have to be keep being performed over this block. So concretely, an acceptance proof is really just a BLS multisig of an accepted block hash in the current implementation of the spec. The proofs are generated using kind of like a leader-elected aggregation protocol. So what that really means is that since Snow doesn't produce these acceptance proofs natively, which is mostly a property because Snow is a probabilistic protocol where your preference can change, so you can generate acceptance proof natively. As these blocks are accepted, it will be kind of like streamed into some process that generates these acceptance proofs. So we'll be determining some kind of like leader schedule similar to how Snowman++ or Proposer VM works, and expect the elected leader to aggregate a proof for the network, and then gossip it across the network to other validators. And so similar to how Snowman++, which is our block production protocol works, if there is like a faulty or Byzantine leader case, other nodes will be elected as like secondary or like whatever leaders, so that eventually you're guaranteed to be able to generate a proof for every or for whatever accepted block you're trying to generate a proof for. So as part of the spec, we're introducing like a few new P2P message types. And so these are the aggregation messages. These are pretty simple. So these are going to be used by the elected leader to generate these acceptance proofs. So what they're going to be doing is they're going to be sending out the signature request, and a node will respond by signing the accepted block and then returning the BLS signature. And then the leader will be kind of like constantly aggregating these signatures until a safety threshold is reached. And then once the safety threshold is reached, it's going to consider that acceptance proof valid and then begin trying to disseminate it across the network. And so to kind of get this acceptance proof to all validators, we're going to use these gossip message types. And so this is very similar to how all the other gossip in our code base works. It uses this like push-pull protocol thing, which is basically the thing that generates the proof will kind of like disperse the information quickly by sending out like an acceptance proof gossip message, which is an unrequested message type. So it'll send it to some like K amount of initial peers. And then nodes will be guaranteed to eventually discover this proof by constantly polling their neighbors using the get acceptance proof request and response, where they'll just keep polling for a proof at some block height, and then eventually be able to discover this message. So I find that like the definition of an acceptance proof is pretty like opaque, like it's just a proof of block acceptance. So we're going to be going over like an example use case that the primary network will actually have on like day one of this being released, which is increasing fault isolation to subnets. So one kind of pain point right now with how Snowman++ / Proposer VM works is that there is kind of this like edge case that can occur where subnets can potentially stall in block production if the P chain is like severely impacted. And so this is obviously not great. So some background information here. Proposer VM implements this like block producer leader schedule for each block height. And this is like an important optimization that we do inside of consensus to kind of limit the range of decisions that are in consensus at any given time. Like prior to this, every single block producer was eligible. So they would all try to produce a block. One block would be accepted and then everything else would be rejected. So you're getting like a lot of wasted operations inside of consensus there. So to produce this leader schedule, each Proposer VM block will encode a P chain height inside of its header. And in that header, we'll generate some kind of like validator set leader schedule off of it. So how this really works is we basically just like shuffle deterministically the validator set at that height. And then we create like a schedule based off of this. What this means, though, is that people who are trying to verify the block will also need to have the reference p-chain height, because you can't tell if the block producer is valid or not according to the schedule if you can't determine the schedule or not at that height, right? And so this is actually possible in some cases. Like you won't have this height if you're lagging behind, for example. And so in that case, you would just reject this block and you would say it's not valid yet. And eventually you may be able to discover this p-chain height as your p-chain that you're tracking locally advances. And so in this example, we have this blue block that references a p-chain height of 10. But if, for example, we have like a height of 5 or something locally, we would say this isn't valid. This p-chain block doesn't exist yet, from what I understand. And maybe eventually, if I hear about this height, I'll be able to verify this block correctly. So what's the problem here? So we talked about how the node can potentially not make progress on the subnet block if its p-chain isn't advancing. This also means that if many validators experience this problem, the entire subnet can stall. And I think we have seen reports, we have seen this bug occur like maybe over a year ago or something. It's not like a common edge case, but it is definitely possible. And so this is definitely not ideal. So after we implement this ACP and we have all of this like acceptance proof stuff inside of the proposer VM, this will change like some of the behavior here. And so previously we would have just failed verification because like locally here we have this like p-chain height 5, and then the reference block is saying there's some p-chain block we haven't heard of called p-chain height 10. But afterwards, since we now know that the heights that are missing, we can just request proofs and blocks for all the heights in between 5 and 10. And then we can verify the proof. And since the proof will tell us whether or not this was like valid based off of like a threshold of stakes signing this multisig, if it's valid, we can just blindly apply this block on top, which is the p-chain height 6. And so once we apply this, we're slowly making progress on the p-chain. And so eventually we should be able to catch up to p-chain height 10. The person verifying the node can always just ask the block producer, for example, because the block producer should be guaranteed, assuming this block was produced virtuously, to have all p-chain blocks between our tip and the, all blocks up to the reference p-chain height. So verifiers can just ask the block producer as like a pretty good heuristic of discovering the p-chain blocks that we're not aware of. But once we apply all of these sequentially in order, we'll be unblocked here. And then after this, we should have much stronger failure isolation guarantees for subnets away from the primary network. And so that's just kind of like one case study example. What's next? We are still finalizing some of our aggregation spec with like how committee aggregation like logic works. And then there are a few like open questions with respect to how we handle state sync, because state sync means that not all nodes will be necessarily having the entire history of blocks, which means that in order to serve acceptance proofs, we'll likely need to keep some like minimum of recent statement proofs around on validator nodes. But yeah, that's a pretty short summary of acceptance proofs and what they're used for. I can like turn the discussion to you guys.
I think one question that I'm really interested to hear people's opinions on is specifically like the prioritization around this. Like I know that we talked about a couple of things with respect to like fault isolation, and there's like definitely other uses for this at like the protocol level, but I'm interested on if anyone is really desiring these mechanisms for anything outside of like stability.
I have a question. Maybe it's going a little bit out of the scope here. So the goal of the acceptance proof is to provide a proof for the inclusion of a block on a blockchain. Am I correct?
That's yeah.
And so the follow-up on that is that the end user would also need some proof for the inclusion of a specific transaction on that block, right?
This can be done, but I think like a transaction inclusion proof is separate from like a block acceptance proof. But there are ways to do this with like Merkle proofs and stuff. Like I think Core ETH like supports this.
Yeah,
So-
I mean, it's over like the hashed block, right? So if you just have the block,
Yeah.
you can just look in the block for the transactions, at least naively that way. I think like C chain blocks and like EVM blocks include like different kind of like sub hashes for how they actually represent their block to like more efficiently provide lookups for things like this. So I think that is still usable for how the proposer VM works, because the proposer VM header is just basically a signature over a few hashes as well. So I think that there's
Yeah. Also, I think another point is that transactions are actually a VM implementation detail. Like you don't even need to have transactions in Avalanche, like technically, actually. So it would kind of make sense that like a transactions route that you may request proofs against also be a VM implementation detail as well.
Yeah. So the reason I brought this up is that, at least in my mind, that would what would the people that are using this feature would really want, right? Like they want to know that they send a transaction and the transaction was finalized and it's on chain, right? No? Yes, no?
I'd be interested to hear people's usage of this outside of just network stability concerns. So I think people have. Yeah, go ahead, Shashank.
I'm working at Movement Labs, so I'm just talking from our use case for this. So technically, we are looking at the concept of finality is important for us because we want to build rollups on Ethereum, and which means we have to post the data to the DA service once it is finalized. So we do want that finality to be reached as soon as possible, and so like it's not just for stability, but it is also for reaching that finality and letting others or like other execution environments know that this is the ordered set of blocks. And in addition to that, there's also a question if this is meant only for EVM particularly, or would it support alternative VMs as such?
I
So
can comment
yeah,
on
go
that
ahead.
last question, if that makes sense. But so I think that this spec would be something that AvalancheGo explicitly would basically handle. For existing EVM things like the C chain or Subnet EVM, it is already possible to generate acceptance proofs for them. But the actual like aggregated proof is not generated automatically. You'd have to run like a relayer. But that capability does exist already for the C chain. But I think that this is a question about having it at a higher level for basically around the proposer VM, which would tie back into like consensus and things like that. So I think that that's So if you on the short term, if you are looking for like EVM specific stuff, I think that there's already functionality in the network that supports this. But yeah, so I don't know if that answered that last question.
I know, just wanted to say that like because we are using an alternative VM, MoveVM. So if it's tailor-made for EVM, that might not really be compatible for the other VMs which might be in use.
Yeah, so the VMs are kind of like the top of the like application building stack that like sits on the top of AvalancheGo. So the Avalanche protocol would actually be generating these proofs like for you. So this is like agnostic to the VM, like as long as this like Avalanche like block interface or whatever is like implemented correctly. these proofs would be generated for you. So it doesn't really care about like it doesn't even know that the EVM exists or not. So this should work for whatever VM that you're working on.
Yeah. So if I understand correctly, then you would still need on your subnet, right, or on your EVM to make sure that your transaction was actually applied to a block, right? And after you have that knowledge and confirmation, you need to make sure that the block was finalized using the acceptance proof, right? And that would be basically the confirmation that you're done with it.
Yeah, if you wanted to like concretely check if your transaction was accepted or not, you would issue your transaction, be told the block was accepted in, you could get a proof for that block, you would see that block, you would verify the proof, so now you know the block's accepted, and then you would likely need the block to provide some kind of like transaction inclusion route that you could get a Merkle proof against or something. But that would probably be the end-to-end way that you would prove that a transaction was included on the blockchain.
I don't know if in their application they really need the Merkle proof for that, right? Or maybe they do.
I guess it depends, but like if you know the block that it's in, if you have a proof for the block it's in and the transaction is there, then that's a proof. If we generated proofs every like n blocks or something, you could just be given a recent block and a proof and have a root against that. But I guess it would depend on how we implement it, if we generate proofs every block or not.
So to be 100% clear here, what you're asking for, Shashank, is the ability to have a subnet that's running with AvalancheGo is it generate a proof that can then be verified on Ethereum or any other DA layer that is not part of Avalanche whatsoever. So it's not just the ability to generate a consensus proof that can be verified as this block was accepted. You can send it to the C chain and say this block was accepted on subnet 1, but you actually want that proof to be able to be verified on Ethereum, Celestia, and any place in some arbitrary ecosystem. Is that right?
Yes, because like currently we are trying to build an SDK where people could just start their own rollups. So we don't really control on which part of the modular ecosystem they might want to go to. So like what we wanted is more generic. But I think it boils down to the concept of some form of finality. So if the block is generated here and then there is some finality on, say, the P chain here, like as in the acceptance proof here, which could be used as a finality gadget is what I'm currently thinking about.
Yeah, that makes sense. So just one thing to clarify then here, what we're talking about, these consensus proofs, they rely on the validator set that's stored on the P chain. So as Erwin said, Cosmos like Light Client, you would also need to be tracking the validator set, which is not actually necessarily included in this design. So in order to do that, if you were to say you want to be launching Avalanche subnets that are able to generate a consensus proof that can be verified not just on Avalanche, but on any other network, then you're also going to need the ability to say your subnet is basically controlling its validator set and controlling all of the state transitions of that validator set to then notify somebody else the validator set has been updated so that it can continue to correctly verify those consensus proofs. Because when we're using Warp or we're using like the signature scheme that we're talking about where it has the P chain state actually available, so it can verify that against the validator set as it's changing there. But what you want to do is verify against any other location. So we have to actually sync that validator set there as well and verify the full state transition, just like Erwin said, the Cosmos like Live client. So there's a slight difference in what we're talking about here, but that's definitely something that this could be modified to support as well. And also seems like a very reasonable request because it's not just the ability to, it's not just the desire to verify these things within Avalanche, but it's actually very specifically to verify them anywhere, which probably requires a bit tighter control of your validators. So that makes sense. That's really helpful.
Mm-hmm.
Did that make sense, Shashank, of like how that part works?
Yeah, no, that makes complete sense. Thank you. I appreciate that.
So I have a question on follow up that, like, I think that this is pretty useful exactly for this kind of use case. But in the case of what was mentioned here of stalling in the case of a P chain issue, right? And imagine that we are in the kind of post ACP-77 world, like where the idea is for these subnets to be sovereign. I would assume that the snowman plus kind of leader selection mechanism should depend on the rules of the validator set of the subnet itself, right? I don't, perhaps I'm wrong, but I don't see it how it like should depend on a state on an external P chain for this leader election. I'm misunderstanding. In other words, like, would that use case go out of the window in an ACP-77 world or not?
So I think in order to maintain kind of like consistent transitions between the validator set, like even in the ACP-77 world, it's not explicitly going to allow you to modify your validator set if the P chain is going down. So like for validator set modifications, it is still expected to be like pushed back into the P chain. So if the P chain is halted, then like the validator set component isn't going to be getting
frozen.
updated.
Okay.
Yeah. So I think the hope is that not everything is frozen, right? Because like you obviously want to like still be able to like issuing transactions and things like that. But in order to basically like verify what the new validator set is, the P chain has to be providing that from like an old, like from the prior validator set essentially. And if that's the mechanism that you're doing this, like if they deviate so far that the old validators are like no longer around, then your subnet is in like a really bad position on being able to like post back. So I know Aaron has had a number of like threads in the discussion for ACP-77 around this specifically. But yeah, so at least as far as the current spec for ACP-77, like that's kind of, I think that's how that ties together.
Yeah, so another way, the way that I think about it, and let me know if this makes sense, is that basically the P chain is maintaining the actual version of your validator set that you're going to be using. And it's just getting injected into those subnets. So when the P chain, let's say it goes down or it stalls for some period of time, then you're not able to send the update to the P chain. So even if your subnet is saying, I want to update my validator set, because the subnet decides what its actual state of the validator set is based off what the P chain tells it, if it can't push that update to the P chain for some period of time, then its subnet is going to be paused basically. Or is it not the subnet activity will actually be able to continue, but it'll wait for that subnet validator set update to be sent and confirmed by the P chain. So the validator set will be locked. And the thing is, during that time, you'll still be able to send transactions, just that the validator set won't be able to change.
Yeah, no, I got it.
Cool.
Thanks.
Just wanted to add a point here. I don't think we are planning like to change or update the validator set instantly. We could think of epochs, like generally lasting a day, and then even the unstaking period is around, like there's a cooldown period of 7 days to 21 days generally in practice. So I do think the updates to the validator set are not like immediate, and they could be a certain delay in that process.
Yeah, so that's why it probably shouldn't be a big deal for many applications. Is for most networks, they have some delay to staking anyways, and it's not really a high throughput. There's no real demand for high throughput of staking updates, which is why for the entirety of Avalanche, the P chain wasn't really originally built to be like, it doesn't have to be that high throughput. There's not those high requirements. And the P chain is relatively fast. There's really not low latency requirements for validator set updates either, because generally there are those considerations. But what you might want, and as part of the discussion on ACP-77 that, as Stephen mentioned, I've written a decent number of threads about, is just the total control of your validator set, so that instead of relying on the P chain to inject it in, you're actually controlling the validator set yourself, and then just notifying the P chain of those updates. And one of the reasons for this would be that instead of the P chain arbitrarily changing your validator set at some point in time, if you're going to be having a Cosmos-like light client that sends the validator set someplace else and notifies them, then you're going to want to have a complete control of that and know exactly when to send those updates. You could do this with the way that the P chain works, but what you'll need to do is have a clear way to send the validator set update so that each subsequent block you're able to confirm this is in fact the validator set that was in charge of this block being accepted. So one way of doing that, the Cosmos way of doing that, is that it has actually control of its own validator set. So any update to the validator set, in order to process it, it has to process the block where it happened. Whereas if you're using the P-chain world, this one sort of like weird case that can happen is that now you have to sync both the confirmations to the subnet and the confirmations to the P-chain. And you don't know where certain blocks were issued on the subnet versus the P-chain. So the P-chain could basically say 5 new transactions have been issued, 5 new blocks have been issued, and now your validator set has changed. Whereas the subnet hasn't produced any blocks in that time. And so let's say if the light client on another network hasn't synced those blocks from the P-chain, the old version of the validator set could still produce some blocks. And then alternatively, the P-chain could sort of say at some point in time, well, now the validator set has changed. So dealing with the complexity there is something that you'd have to deal with. And this is one of the reasons I put on the thread is why I think actually just the subnet controlling its own validator set and then only notifying the P-chain instead of relying on it completely would make that type of process much easier. Because that'll be the thing that you have to handle is this Cosmos-like light client that's not only handling the proofs, but is also handling the validator set updates and the proofs of them each time.
I have another question on the other topic actually, but it's like this seems like to be kind of on the order of number of validators communication, right? Is this is this any bottleneck? Are we planning to do this on every block, or is it like every X number of blocks and things like that? Because yeah, you know why.
This is a great question. So I think like as far as this ACP, like it may make sense to separate it out into 2 components. One being like making it so that the validator set basically serves everything that's required in order to generate these acceptance proofs. Wouldn't immediately make it like possible to be used for things like the fault isolation or things like that. But it would potentially unblock the alternative use cases. And then thinking about how we actually go to generate these things, because as you mentioned, it's potentially an expensive operation too. So I know that we had talked a little bit about like having like a some leader to like that gets elected that's job is to like aggregate these things. There was some conversations about I don't know if anyone read the Vena kind of like consensus alternative that Patrick had talked about, but essentially it works using aggregation committees, and that idea of aggregation committees is definitely like useful here to reduce the complexity required on any given node. So it's a little complicated on how you would like generate these efficiently, because when you have like BLS multi-signatures, you can add them together, but you don't union them together. So if you have a multi-signature from A and B and a multi-signature from B and C, it'd be great if you could take that to be a multi-signature of ABC. But what ends up happening is you have a multi-signature of A to B and C, which complicates the verification. So there's definitely like still some open questions on this ACP about the aggregation, and I think there's actually an explicit to do in this ACP to like go more into the aggregation rules. But if we wanted to like have a earlier kind of ability of unlocking acceptance proofs, I think that that's actually extremely well defined. So I'm not sure if that would be enough for people. Like, it would definitely be very possible for us to have basically a server, like add into AvalancheGo the like server requests, and then implement a like relayer-esque implementation that can generate acceptance proofs for any arbitrary chain. So that would definitely be like the fastest way from 0 to 1, not including the aggregation logic explicitly in AvalancheGo. But I don't know if that would kind of solve, or I don't know if that would be enough for people to use it, or if there'd be interest in that, or if instead we should, it would make sense to focus on the full thing to provide, the fault isolation and things that we talked about there. But like, I think that is a very tractable and honestly very reasonable thing to get in on a short timeline, if that would work out for people. So I don't know if there's any thoughts there on if that would be like a workable design or not in the short term. Or if that wasn't clear and I was just rambling for the past 2 minutes, that's also a fair critique if that's true.
No, I think that was pretty clear. You're basically saying that we could split the ACP into one ACP that focuses just on serving the acceptance proof for any chain, like arbitrarily, and then another one that's more detailed, talking about like how to provide like signature aggregation on like explicitly within AvalancheGo instead of just like running it on a separate server.
Yeah, basically like adding the ability for someone to generate an acceptance proof versus generating the acceptance proof. Adding the ability to generate it generically to any chain wouldn't be much work at all. And we could also like actually implement that like spec as like a relayer outside of AvalancheGo that you could run on any chain. But then like actually embedding that relayer-esque functionality in and like doing that on a consistent basis for the P chain and things like that to basically like provide that fault isolation is where it becomes more complex. And when you would start to wonder like, how frequently should these signatures be produced by the network? Like, do we, want to introduce epoching onto validator sets so that like we explicitly don't have to provide as much of this work? Like there's a potential, like there's a lot of questions that I personally have about like the aggregation design. So I guess is how I would say it. But if we're just okay with having a separable relayer that like that relayer has like higher bandwidth usage in expectation to produce these signatures, then that's reasonable, I think.
Yeah, I personally think a relayer is totally fine here, especially as a first pass and especially as a way to get it done quickly. Is just not entirely necessary. And the real thing to unblock is just to make it possible. I would even argue that as long as there's anybody can be the off-chain relayer, it is reasonably decentralized. It's just that it's not taken care of by the network itself. But it's so cheap to serve these requests. Like you literally, for just bootstrapping, it's like a get block request, like signing a VLS is so cheap. It really just doesn't.
Yeah, there's more expensive methods on the PvP layer right now than this for sure.
Yeah, absolutely. So I think an off-chain relayer is perfectly fine. It's very, very easy. This is just the easiest way to get it done as quickly as possible. And then, so I think that totally works. And then the questions to me are really, should it be done by Avalanche? Is it easier for it to be done by AvalancheGo? Which I think the answer is most likely yes. Or is it easy also to set it up within the VM in the same style that the C chain and Subnet EVM have done it? That's actually a question.
So I actually think if the plan is long-term to like use this to provide fault isolation, I would argue it needs to be in the AvalancheGo level unless we're pushing the proposer VM on the other side of the gRPC boundary, which is again a very large architectural change. So like I think if we were to add this like right now, like the existing flow for like the C chain is how you would implement on a VM level, right? Yeah. So like it's not particularly specialized for the C chain, but like that it is like implemented there, right? So like you would have to like implement it in some other place, and maybe we could add a library, but it wouldn't be kind of out of the box. But I think this totally makes sense on the AvalancheGo level, especially if you want information around the proposer VM header, because if it's in the VM, you're not really explicitly even told the proposer VM information right now.
Yeah. I do think it probably makes sense to, I think of the proposer VM as very much part of the VM as opposed to part of the engine, because I like the idea of other VMs being able to decide that mechanism themselves. especially if you're a project that's like forking something else or using something that already exists. Or if you just want to more explicitly manage your own validator set, as like for this Cosmos like line thing is potentially required, then you might not want to use the proposer VM, in which case maybe this doesn't take care of it for you. But if we could also just provide a package in Golang or an example that shows exactly how to do this, that's helpful as well. I think like the requirement is very clear, is we probably want to do this inside of the proposer VM for fault isolation and have a clear package that can be imported pretty much anywhere to handle this. And we also want to have a very clear path for this Cosmos like client to actually work, where VMs are able to either using the pchain and their own VM, but actually track the validator set so they can sync those updates to an external network, because there's increasing demand for that. It's always been something that people wanted. But I think that'll be very important, because that's the distinction here.
Are there any other open questions? In that case, Shashank, is there anything else from you? Like, does that proposed solution help you accomplish what you're setting out to do with movement?
Yeah, I think fundamentally we are looking at two things here. One is managing the own validator set, because we might have our own native tokens, and so that's one of the goals. And the other big question was regarding the finality. And I do have a question on, even if I use acceptance proofs as a mode of finality, like that does mean that the block has to be generated first on a subnet, and then the proof has to be accepted on the the main chain, I guess. So what is the latency I could expect to reach that finality if I'm using that as my finality gadget?
I'm sorry, I just want to clarify. Did you say the acceptance proof getting accepted on the P chain?
Yeah. Is it on P chain or C chain? I'm sorry about that, but
so currently subnets don't post back any acceptance data to automatically. You can obviously post anything you want anywhere. And so the C chain does provide the ability to verify like block hash warp messages. And so if the hope is that that would be able to be like included, that's definitely that is something that exists.
Maybe the question is, then if I'm posting it onto an external DA, do I expect the DA to do the verification? I think which might not be the case. So I'd expect some verification to be done before posting it to a data availability service, in our case, which would act as a proof of finality for the given validator set. Is that a good way to look into it?
So was your question like, what is the latency for the proof to be generated? Is that your question?
Yeah.
Oh, okay. Yeah, I mean, it would depend, because I think it would be a function of a few things, like one of how frequently we produce proofs, and then the actual aggregation protocol, like whatever we end up deciding on. I can't imagine it would take more than like 30 seconds, 15 seconds. Like I would imagine it would be pretty quick. But there would be a minimum amount of like aggregation time, because it's not happening like during consensus, it's happening like after consensus. But like Stephen mentioned, like these proofs aren't posted in the C chain or P chain. It's like your block's accepted, and then the VM is not generating the proof, but you could think of the proof as being a part of your chain. And then you can share the proof with whoever you want. It would be an okay way to think about it. But I can't imagine it would take more than like 30 seconds or 15 seconds or something in that range. But I don't know if that's like what latency like people are going to require for this.
On the flip side of this, like, so in the time using Snowman consensus between like having a block be like verified locally, so like first discovered and like accepted, is typically around 1 second. After it gets accepted, in the world where we're not like, we just basically expose the ability to generate these aggregated signatures, that node would immediately be willing to sign the acceptance certificate for that block. So then the question is basically like how aggressively you tune the relayer, I suppose, because like, if you have this like kind of a like elected like aggregation committee like mechanism, like that's gonna like incur some things, and you have to like, because it's actually part of the system, you have to like make sure it's really like robust. But if the relayer is just trying to go as fast as possible to generate these proofs, like I think it should be like really fast, right? Because like you have your like 1 second block acceptance time, and then it's basically just however long it takes to contact the validators to get the signature, verify them, and aggregate them. So
Okay. Yeah, I think that makes sense. Yeah.
Yeah, in the happy case, we could probably get like under 5 seconds, I guess, under 10 seconds. Like I don't think it should be like minutes or something like that, but I would guess that like order of magnitude.
And what signature scheme does it currently support?
it's going to be BLS.
Yeah.
I'm actually not too familiar with like data availability, like roll up L2 style things. So like, I'm not necessarily sure I understand all of the intricacies with respect to like what needs to be verified by the thing providing DA. My understanding was that like you would typically expect that base chain to be like verifying the acceptance proof over like the DA that you're, or the data that you're sending to this DA, like, but I'm not an expert in that kind of stuff, so I don't really know.
No, I mean, that's really fine. I think we're just looking for some form of finality there. Just the data is just which would be posted on DAs, would just probably be the transaction data. The like basically the call data for the like reproducing the state in a compressed format.
Okay, so I think it makes sense then for us to kind of consider this in two parts. One is the server side stuff, which would unblock any usage on the application layer. And then from the stability standpoint, we can dig into how the aggregation works and the rate at which we would expect to produce that for something like the primary network. Seems like we're pretty aligned on those mechanisms.
Cool. Yeah, I think that makes sense.
Okay, great. I think we can keep the server-side application as this ACP for 75, and then we can make a new one for the signature aggregations. Does anybody else have any other questions? We still have a good amount of time left, so anybody can ask anything they want.
What are your favorite kind of chips, Meg?
My favorite kind of chips?
Yeah. Richard, what's that? Come on, that's a good question.
I don't think I've had a chip. I ate a plantain chip yesterday. That was pretty fire.
Oh, plantain chips are good, yeah.
Yeah. Mm-hmm. I didn't mean anything. You can't ask anything. Maybe we should set some boundaries here, but
yeah, we're going off the rails. If we're talking about chips, it might make sense to
See everybody.
Thanks for joining, everybody. This recording will be available on the ACP discussion that was posted in response to this meeting being planned. So thanks again. See you next time. Bye-bye.
Thank you.